Are you able to see the PPT? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Oh, fine. Yeah. So this is about device physics for engineers. So we need to understand what is it, why it is important, and what are its content. So electronics, we like I always like to make this statement. Electronics has become omnipotent, omnipresent. So I hope all of you understand the meaning of omnipotent. Omnipotent means or powerful. Omnipresent means present everywhere. So actually, in fact, the most commonly used prefix is E. So electronic content is there in almost everything. So if you look at the way we have evolved, so we have started from the Stone Age to the era of iPad or whatever. So there is the this is a evolution of human technology, you can say, or it is in fact that helps us our evolution also. So it is whether if you talk, you can talk either in terms of technology or human progress. Both are linked. So today, earlier these tools were used to help us for enhancing our skills, basically. For example, if you are not able to fly, we built aeroplanes. We were not able to move in the water, we made ships or boats or whatever. So like that, so it was enhancing our skills basically, or our limitation. To overcome our limitations, we were using the technology. Now increasingly what we are doing is we are trying to replace ourselves. So this is popularly the catchword at present, that is IoT, or increasingly you are going towards IoE, that is Internet of Everything. So you are interconnecting everything and controlling. You are taking away the control from yourself, and it is given to the machine. So that is why today we talk of artificial intelligence, we talk of machine learning. You are training the machines to do the work for you, and so that you can replace human intervention, or you don't need human in using. So this is the kind of progress we have made. We started with enhancing our skills, and today, and there the thought process was ours. Now the decision making or the thought process is given to the machine. So you talk of artificial intelligence, and which is gained through machine learning and things like that. So today this era is basically of artificial intelligence and machine learning. Anyway, now, before going into this, all this was made possible by our engineers. So now we need to understand what is the what is what do we mean by an engineer, and what is especially when we talk of an electronics engineer, what is role of an electronics engineer, and things like that. Anybody would like to define an engineer? Hello, can you give me a definition of an engineer?
Engineer who implements the laws basically, which are made
Okay.
by the scientist and all.
Okay, so here I would like, I mean, there is my favorite definition of mine. So I will try to use that. It is, I don't know how many of you have heard of Anand Agarwal. Have you heard the name Anand Agarwal? Hello?
No, sir.
Hello?
No, sir.
No, sir.
See, he is a professor at MIT, and he's but well known for starting of MOOC. What is a MOOC? Hello?
Don't know, sir.
Don't know, sir.
You have not heard of MOOC? MOOC,
No, sir.
Massive Online. open course. Everybody is talking of today. Everybody is talking of. Just a second. Somebody is trying to join. Yeah. So all this, see, with the COVID around, everybody is moving towards the online courses. So he was one of the founders of this. So this is one platform where he has created. He is a MIT professor. So in MIT, and he has started this massive online program which, for the basically for the engineering, and that is EDX. There is one more online course programs, that is Coursera internationally. Indian government also has initiated online courses. What is that is known? What is the name of the MOOC program started by government of India?
Swayam?
Yeah, SWAYAM. SWAYAM is that is starting from school to higher studies. I mean, higher education. You can do online. So that is the SWAYAM. That is a very recent phenomena. Much before that, IIT Bombay had started similar to EDX. IIT Bombay had started IIT VX, something like that. They named it. It is similar to, they are using EDX tools for that. EDX created by Anand Agarwal's. So he's the founder of this, or and the CEO of the MOOC program initiated by the MIT. So he, in his class, one of his classes, he has used a definition of engineering. So I will just have a quick, I hope things will be fine for us. So please listen to this, his lecture. If you have any issues, please let me know.
Ask ourselves is, what is engineering? Okay, how do we define what is engineering? Well, the definition I like to use is one put forth by Steve Centuria, one of our professors who's now retired. He defined engineering to be the purposeful use of science. All right? So then, what is 6002 about? So 6002 is the first course in engineering, and I like to view 6002 as the gainful employment of Maxwell's equations. Okay, many of you have seen Maxwell's equations before. Most of you should have. And they're hard stuff. Okay, 6002 is all about teaching you how to simplify our lives, make things simple. So we can gainfully employ Maxwell's equations, gainfully employ the facts of nature to build very interesting systems. So let me show you how that transition is made. So there's the world around us, nature, and so we make some observations in nature, we make measurements, and we can write down large tables of measurements. So for example, we can take objects and measure the voltage across them and look at the resulting current through the elements. So we may end up getting a bunch of values such as so we start out life with making measurements on what exists, and we build a bunch of tables. Now, we could directly take these tables, and based on our observations in these tables, we could go ahead and build very interesting, engineer interesting systems that help us out in day-to-day lives. But that's incredibly hard. Imagine having to resort to a set of tables to do any kind of useful work. So what we do as engineers is we first layer a level of abstraction. Okay? We look at all this data and somehow layer an abstraction such that we can simplify or much more succinctly put in a simple equation or in a simple statement what these numbers are telling us. Okay? So for example, our physics laws. So laws of physics, for example, are simply abstractions. Laws are abstractions. So these sets of numbers can be codified by Ohm's law, for example. V is equal to Ri, the voltage current, relates to the resistance of the object. So V is equal to Ri is a law that succinctly describes a set of experiments, okay? And replaces a large number of tables with a very simple statement. You could call this a law, or you could call it an abstraction. Okay, so you've seen laws of physics. Call them abstractions of physics, if you like. Similarly, there are Maxwell's equations, and so on and so forth. So this is what is. Okay, this is out there. Okay, and our laws and abstractions describe the properties of nature as we see it in some succinct form. Now, if you want to go and build useful things, we could take these abstractions, take Maxwell's equations and go and build things. But it's hard. It's really, really hard. And what you will learn at MIT is this place is all about simplifying things. Okay, take complicated things, build layers of abstraction, simplify things so that we can build useful systems. Okay, even in 6002, we start life by making a huge leap from Maxwell's equations to a couple of very, very simple laws. Okay, I'm going to show you that leap that we're going to make today. So the first abstraction that we layer is called the lumped circuit abstraction. Okay, and in the lumped circuit abstraction, what we do is we
Hello. Yeah. Hello.
Yes, sir.
Was it audible? Was it clear?
Yes, sir.
Hello. Could you make out something from that presentation?
So the purposeful usage of science is called engineering.
Yeah. See, actually, see, there are, we will be talking of, the relevance of what we have seen will be evident as we discuss further. See, actually, we observe nature, so we see certain behavior from the nature. For example, the example he has said, you change the voltage across something and you see a pattern in the current. You can make a table. So that can be abstracted in the form of see, for example, Ohm's law. That was V about which he was talking. V is equal to IR. So instead of writing the whole table, you have written V is equal to IR. That is an abstraction. Similarly, other other abstractions are also possible, which you are familiar, like across the capacitor. If you change the voltage, a different thing happens, and then again you can abstract it. See, you can write it in a table form or in an abstract form. Abstract form means you can get a formula which represents, you can replace that table with a formula. So that is one level of abstraction. And the second thing is, once we have that abstractions, or next thing is, as the definition goes, we can take advantage of these laws to make useful systems. So that is the engineering is all about that. There are physical, chemical, and other laws which are abstractions, and then you take advantage of those laws to make useful devices or gadgets or whatever you may call. So that is the engineering is all about that. Purposeful use of physics. Yeah. Now let us go back. So the full lecture, if somebody is interested, you can watch it. The link is given in this, or it is posted in the Piazza page, because as electronics engineers, it will be interesting to watch the full lecture. It's around 30-40 minutes. You can watch it leisurely and try to understand, because he will be talking of different levels of abstractions in electronics also, so you can just see that, like, so that will be interesting. So anyway, I am not going to those things right now. So as an electronic, so we have seen in general, an engineer's job is to convert the physical laws into useful gadgets. So an engineer, electronics engineer, will be expected to obtain electronic gadgets. So then one thing we have to understand, whenever you talk of an engineering a product, it will be involving use of multiple laws. It's not that only one law will be used, so it will be a multi-physics problem. So in the use for engineering the products. So I need not mention what are the kind of gadgets we are talking of. We are all flooded with all types of electronic gadgets. But one thing we need to understand, how all these gadgets are made. So when you talk of a gadget, the fundamental thing is, we are talking in terms of different functionalities. For example, if you take a cell phone, it has various functionalities. You can use it for a voice call. It can be used for image capturing, then video capturing, then processing, then transmitting it. So that is again another function. Then for listening to music, then browsing the net, all sort of things can be done. So that is the functions of the gadget. So now, how the functions are obtained? Functions are obtained using circuits. And then what is a circuit? Circuit is, you have basic elements which we have seen, we are aware, and a combination of those elements or devices will give you a useful circuit. So this is, so that is like a sentence is a group of words which make sense. Similarly, a circuit is something, a combination of various devices or elements which gives you a certain functionality. For example, a certain combination of transistors and resistors and capacitance will be give you amplification. A certain other combinations may give you filtering action. So there, similarly, other mathematical functions can be also obtained, adders, subtractors, or multipliers, and different functionalities can be obtained using circuits by the different combination of devices. So that brings us to devices. So this is the first abstraction level which is used in electronics, that is the devices. So I'm trying to uh, bring in the importance of devices in the larger context. How, what is the role of devices, and understanding of devices helps us in making large systems. So this is the first level, like just immediately after the physics laws, we come to devices. That is the lowest level of abstraction. So now a little bit about abstraction. So this actually, mathematics is all about abstraction. Say, for example, 2 plus 2 is 4. So the beauty of this abstractions is it is immaterial. You can apply it at various, see, for example, this 2 plus 2, 4. You can apply it to oranges, apples, whatever. It makes no difference. So it is a conceptual process where general rules and concepts are derived, and then it can be used widely. And then scientists generally use mathematical abstractions, and the advantage of mathematical abstractions is then you can do the mathematical manipulations, so mathematical operations can be carried out of the math, and then it can give you, it can help us in design. So that is the idea. So now whether it is designing of a house, whether it is a designing of a computer, whether sending a space, designing a space shuttle, it is a physical problem, and that problem can be converted into a mathematical problem, and the solution of that mathematical problem will give us an engineering solution. So you, in fact, you are working with a mathematical model of that system, and then you develop the design around that, and that way it will help us. So and we have that is something beauty of our human mind or a human brain, that we have developed uh, highly evolved mathematics, which can be used for engineering the products. So once we have the mathematical abstractions, then you can use available mathematical tools for, and then increasingly many of these complicated mathematical uh, problems can be handled by computers. So you can use take advantage of the computer. As you go further, you will be seeing, and already you might have seen use of computers in solving complicated problems. In fact, every problem today, whether it is weather forecast, whether it is engineering, designing a product, everything is converted into a mathematical problem, and then the rest of the things will be taken care of by the computers. So, and these are some of the other advantages of mathematical abstractions. Then the functionality and behavior prediction before actual production is possible. Then you can have a lot of insights. This it will be evident as we go further. Immediately you may not be able to appreciate it, so you can get a lot of insights, save time, saving time. So it will give you cost reduction, reduces time to market. That is very important in electronics. And then you can have modification and improvements. Then you will have you can have propose new devices, and then new logics or circuits, and the new fabrication techniques, etc., can be also proposed. That these are some of the advantages. So this is the hierarchy which we are talking of. The functionality is obtained by circuits, and circuits are obtained by combination of devices, and devices are selected by their characteristics. See, for example, you know that diode will have certain features, or the IV character. When we are talking about the characteristics, it is the IV characteristics which we are talking of, the current voltage relationship. So we are applying a voltage, and what kind of what will be the nature of current flow, etc., for the given voltage or the given electric field. So and so the different devices will have different electrical characteristics or IV characteristics. So one need to, the first level is looking into abstractions of in device characteristics, and then once we know the abstractions in the device characteristics, or then we can design your circuits around that. For example, we have seen diode has certain characteristics, a transistor has a different characteristics, a resistance has some sort of which is different from the diode or transistors, and then similarly capacitors, inductances, all these electrical elements have different IV characteristics. So we can take advantage of those and then combine them and get different circuit functionalities. So that is an important thing. So this is what some typical abstraction in the characteristics. Say, for example, you can see the diode has ideal diode. I'm showing it here. This is ideal diode or ideal switch, you can say. When it is on, it has large amount of current is flowing, and then when it is off, zero current is flowing. This is an ideal switch. And then if you look at the diode, it is somewhat similar in characteristics to this switch. So you can replace this switch with a diode, and then diode, again you can see that it can be, again you see, once you see the characteristics of a diode, you can see that under certain bias condition a large amount of current flows, and when you change the polarity of the voltage, the current is almost negligible. So it can be used for rectifiers, or then it can be used as a switch. So various applications, that is for the, that depends on the engineer's creativity. They can find all sort of applications using this. Similarly, this is a kind of resistance characteristics you have. When you increase the voltage, the current is increasing proportionately, and things like that. So this is another abstraction. I mean, I'm not shown all the device abstractions. Some typical examples only we have selected. And then you have the transistor characteristics. So there are three variables. Fixing one variable, if you change other two variables, you will see that there is a typical characteristics like this. So important thing is any device, for example, giving this kind of characteristic can be used as a switch. Any device which is giving the characteristic similar to a diode can be used as a wherever the diode can be used, you can use that. For example, it can be used for rectification, it can be used for switching, or it can be used for clipping. All sort of applications can be thought of. So the important thing is not diode. What you need is a device having this kind of characteristic. Similarly, if you have any device which is having the characteristic similar to this, that is the like the transistor or a vacuum tube or whatever be, if it is showing the characteristic similar to this, it can be used for amplification purpose. Then again, this like we have, as you if you look into the history, we have started with vacuum tubes, we have ended in MOSFET. But the basic characteristics, whether it is when we are using it as an amplifier, whether it is a vacuum tube, whether it's a bipolar transistor, or whether it is a MOSFET, the characteristics are similar actually. So the basic characteristics remain the same, but there are other some advantages we got. So that is why we have replaced vacuum tube with BJT, and then later on BJT is replaced with the MOSFET. That is the beauty of this abstraction. So we need to understand in that context. Not don't get stuck at that. Okay, for amplification, I need vacuum tubes only. Or I need to use only, I can use only MOSFET for amplification. No, tomorrow you may come out with a new device where the characteristics is similar. Then again, I can replace even the MOSFET with that particular device. So that is the beauty of this abstraction. So you should get stuck with the abstraction, not with the device. So for amplification, you need certain kinds of device characteristics. So any device which gives that kind of characteristics can be used for amplification. Or so similarly for a switch, because basically when we talk of electronics, we need two branches of electronics. One is the analog electronics, where we talk of amplification, filtering, etc. And the other one is the digital electronics, where we use Boolean algebra, that is the binary. So you need two variable representation. So two variables 0 and 1 can be represented using switches basically. So in very often we call them as gates. Gates are open or closed or on or off conditions of various ways. So either 0 or 1, various ways. So you can use the most of the Boolean implementation can be done using those gates or switches. So you need these two types of elements. One is so most of the digital electronics depends on uh, gates. So you can build gates using switches. So if the faster the switches, the better it is. So you'll the attempt will be always to have better and better switches and faster. So that way you can improve, and the power consumption should be less, and all those considerations will come. So you need basically switches for making the building the digital systems, and for analog you need amplifiers and things like that. So how we have reached, you see, all the basic abstraction remained the same, but we have used various elements or various devices. So electronics started with the vacuum tube era. So we had the leftmost side, we have the this, you can see this is a voltmeter. I used to use this kind of multimeter when I was in BSc. That is a vacuum tube based multimeter. We were used to call it as VTV, vacuum tube voltmeter. Then this is a TV set with valves. Then this is a radio with vacuum tube. So this is a typical valve size. Almost all the device systems you are seeing today, not all of them, so most of them, they're like radio, TVs, etc., were available. Even the multimeters and all those things were available using vacuum tubes. In fact, even we have created a computer also, ENIAC system. So it was 1956. This is a picture of that. So you can see that there were around 20,000 vacuum tubes inside this, around 7,200 diodes, and then you have the relays of 1,500, then resistance 70,000, then capacitors around 10,000, and then you had more than 5 lakhs or 50 lakhs hand soldered joints. So the weight was around 27 tons. You can just imagine the computer, the weight. And today you are carrying it in your, putting it in your pocket and you can move around. So it used to be, and it is much more powerful than though this ENIAC systems. So you can see the power. It used to was 150 kilowatt. And most of the time the tube burnout was a big issue. So it was always there was always a problem. We are always busy replacing the fused tubes, etc. Yeah. So this, but we have gone up to the developing an electronic computer with vacuum tubes. So now so second wave or second revolution came with solid state devices. So you had 1947. You had this point contact transistors were developed, and this is a first point contact transistors. You can see the size, and you have a semiconductor block. Then you have make a contact with this. So this is a base element. So this is you can see this picture. So this is the this has changed the way the electronics was done. This is one of the most important development as far as the electronics is concerned. That is the semiconductors or the solid state, popularly known as the solid state device era. So now, with the most of the electronic systems were which were based on vacuum tubes were replaced by transistors over the next 20 years or so. That is between 47 to 1959-60. Or most of those things were replaced by transistor. You have instead of vacuum tube radios, we were having transistorized radios or solid state radios. Then TV was replaced. Then even the computational systems were also developed during that period. So in between 47 to 60, we have seen a huge leap in the solid state devices. Actually, initially started with the germanium, and then some silicon based devices also started coming into the market. So it started with these three gentlemen from Bell Telephone Laboratories. Now, at around sometime around 59 or 60, you have a new development happened, which brought in the integrated circuits. That is integration of all this passive and active element into a single substrate. Earlier, we have seen whether it is a vacuum tube or whether it is a transistors, you have different components, and then you have wired joints, you have the soldering and then things like that. So interconnections were different. The devices was, it maybe on a PCB, you have the devices fixed, and then interconnections were made through the wires, connecting copper wires or something was used, or you have a layer of copper and things like that in a typical PCB. Whereas 59 also, Jack Kilby came out with this idea of integrated circuits. That is the integrated circuits mean you are integrating the passive and the active element into a single substrate of silicon. Or it was not silicon in the first case instant, it was germanium. Jack Kilby used it germanium. Later on, Robert Noyce used the silicon substrate. Which, so that and then you have a different hierarchy today, which we talk. So that was the starting of the solid state circuits. You have seen the solid state devices era, 47 to 60. Then we have seen, which we talk of even today, that is the solid state circuit. So the whole circuit is developed on a single substrate. That is the meaning of solid state circuit. So ICs or microchip, or the other name is the microchip because of the miniaturization. They are sometimes known as the microchip. So that brought in a huge revolution. The IT revolution was brought in. So today we have this kind of hierarchy. You have a system, whether it could be a computer or any system. So you have boards inside, then you have chips, and the chip, within the chip you will have various blocks, and these blocks are made of logic gates, and the logic gates are made of transistors, and transistors are implemented using solid state material like silicon, things like that. So this is a kind of hierarchy we have today, we talk of. So this whole thing was made possible by a new material, or the semiconductor material. So this is the basic introduction to our this course. So now we will be looking into the properties of the semiconductor material. What is so special about this semiconductor materials, and and then the first part we will do that, and the second part what we will be doing is we will be looking at into the various devices and how they have that, because don't forget our original goal. Our original goal is to get the abstractions or the device abstractions or device characteristics which could be used for designing the circuits. We may not do any design of the circuit, but in another course you will be doing that. So this background is very much essential. So first we will be seeing the materials which can give us those devices. So what are the basic properties of the materials and how they can be used to make devices, and then we will see the characteristics of the devices. So basically the IV characteristics, and we will obtain the abstractions for those devices, and then a little bit idea on the implementation of it in circuits. So that is the way we will be going about it. So I think I'll stop my presentation here today, and the next session we will be discussing about the materials, the semiconductor materials and their properties, how they have those properties, how they are different from other materials, and things like that. So now few quick questions. Hello.
Yes, sir.
Yeah.
Yes.
Sir, I wanna ask that you are saying कि electronics are everywhere. Electronics things are right now everywhere.
Hmm.
But we can see the students, mm, less students want to come into the electronics. We can see in bachelors and masters and all.
No, that you are typically looking at. See, today there is that is another crisis actually, which was brought in by electronics. Actually, we have made think. See, like when you talk of electronics or the IT, or you have two parts. One is the hardware, and the other is the software. Because the overemphasis, the backbone is the hardware. If without the hardware no software will work. But the problem is we are giving too much emphasis to hardware, sorry, software. So that is why the issue has come. It's not about there is a shortage actually. The problem is there, that is a different problem actually. The problem is we don't have see, we have a huge engineering output. I mean, a lot of engineers are produced, but how many of them are skilled actually? And then as I told you earlier, many things we are not trained to evolve with time, like the market requirement. We are given a special, suppose you are given a course and you think that that course will be directly applied to your uh, the job you are looking into. So that doesn't happen. You are giving a certain training, and then on that should be a foundation only. So using that you should be able to go further. So that is why the problem. It's not a crisis, because there are huge applications of electronics, and it is ever increasing only. It's not going down. So the crisis is because of something else, not because of lack of opportunities. Opportunities are immense. That's what my take. You can differ with me there, but it is not because we are slowing down. The electronics development is not slowing down.
Yes, sir.
Yeah.
I agree with you. More and new devices are being created by the companies, but actually the problem is we are not getting with the innovative ideas and
Yeah. And
that
Yeah. So that is the issue actually, because there are a lot huge I mean, of course, human creativity, we were talking of replacing humans and all those things, but human creativity has no replacement, so that is still there. So you have to come out with but our education doesn't produce that kind of thing. See, for example, suppose you start with the schools or colleges, you are given certain set of experiments, you are doing that monotonously and you don't gain anything by that. The only thing is you will pass exam. I give you a problem of designing an amplifier. You will design an amplifier. You don't know what for it you are doing all those things. So even from the school, it is like that. See, I've been taking classes of some school students recently, just to kill my time. I found they don't understand why they are doing all those things. They are simply doing like that's all. So that is the problem. From the right from the school days, you are trained like that. So that has to go. So that is why, and then unnecessary rush for people who are not interested in doing the particular course, they will do it, and then they don't have any interest. See, I have seen in India, I have seen very less number of people who are satisfied with their job, because they ended up because of some status or various other reasons. Not they are really interested in that job. They will be always crying. So that why, if you're really enjoying, because they will be looking at the, you go to any office or anything, you will be seeing the 9 o'clock, and then they will be looking at watch for 1 o'clock. And if you are really working, you won't look at the watch. You'll be just working. So that means they are not enjoying. So that is a different problem altogether, actually. I hope the new education policy will look into those aspects and some improvement will come, but we will not be seeing that. So for me also, it took so many years to understand all those things. But then some of the things I tried to change in myself and started enjoying the work I am doing. But then those kind of introspection doesn't happen with everyone. So, but unfortunately, our education doesn't provide that. So we have to do it yourself. Actually, self-help is the only solution. Yeah. So don't think that there are less opportunities. I don't agree to that at all. There are a lot of opportunities for a creative. So this is a basic training is there. Then with that you can uh, move on. Actually, you can. I mean, don't depend that somebody will come and give you a job. You can find out your own job also. There are. It is possible today. You can do that. I don't know. Bhaskar is not satisfied with my answer.
No, sir, I am satisfied.
Yeah. Anything else? Any more questions? Hello.
Yes, sir.
No, sir, not now.
Yeah. So in the next session, we will look into the semiconductors. Basically, we will be looking into the band structure of materials and how they are important for uh, giving the properties to the material. So that is that aspects, and then we will focus our attention to semiconductors, especially silicon and its properties. So that is in the next session will be devoted to that. So I have created a Piazza page. Those who have, I hope everybody, all of you are able to join that. In case of any problem, you can mail me or any issues. So right now I have only posted the syllabus and some all this Anand's Agarwal's that lecture is available there. You can get the link from there. Then some of these IC fabrication steps are from those. All of them are available in YouTube. So I have given the link from YouTube only. So those things, and then another this one site created by an alumni, that for discussion group EVLSI, you can join that also. So all those links are available. Then this EDX, see, you have a lot of time, so you can join some of these Coursera or EDX courses apart from the regular courses which you are doing, because I assume that you have a lot of time. You can find some interesting courses related to your the subject area, or beyond that, someone of the management or somebody is interested in law or something, so they can, all sort of courses are available, and mostly they are free or not very costly. Most of you can afford that. So you will get. I mean, they are mostly run by the reputed universities abroad, like US and Europe. And Swayam also, of course, I'm not a great fan of Swayam platform, but because got used to this Coursera and EDX much before. So my personal recommendation is Coursera or EDX, but one can always go to the Swayam also. Yeah. So okay, so